All right. Hi, everybody. We are eyeMouth. Our project is a visual speech transcription system for deaf and hearing impaired. So, in general, we are creating a conversational aid for the hearing impaired that works better in loud environments. We're doing this because there are not many visual-based devices existing for this purpose, and utilizing lip reading allows us to overcome any background noise that may be present. And through this, we aim to benefit those with hearing impairments. Our team consists of myself as a team leader and hardware lead, Manu Luzencourt in our hardware design, Krish Patel as our software lead, and Nicholas Portanova as our software design. So the motivation behind our project is we wanted to create a conversational aid that works very well in high background noise environments. Current systems, such as hearing aids, cause difficulty when distinguishing between background noise and people in a conversation. A visual-based system would not be affected by this, um, and we propose to accomplish this by using lip reading. Current companies that do similar projects can be seen through like Demand AS. They're a global market leader for development and manufacturing of products such as hearing aids, which people with hearing loss utilize. MedEL, which is a global innovation leader for hearing loss solutions, and they're directed towards physical implants. And lastly, we have Nuance Communications Incorporated, who are a pioneer and global leader in conversational AI for a variety of industry applications. When designing our system, we had several things that we considered. First, being a lip reading camera that was physically attached to a pair of glasses. This would create a low-profile implementation of our system for the user to wear. We deemed this undesirable as connecting the rest of our components along with glasses would make it uncomfortable for them to wear. We also considered using a separate display instead of connecting to a smartphone app. This would help the usability as they would not need to pair a phone, but we deemed this undesirable as it requires the user to carry a separate display in addition to their own device. And below, we have our AHP, in which we compare existing solutions such as hearing aids, the Translate app that is currently available on iOS devices, as well as CART, which is a stenography service. And we compare them through traits like comfortable, user-friendly, adaptable, and cost. And we deemed our system the most preferable. So overall, we will implement this technology in our project as a handheld device, which utilizes a camera and a portable power supply. The device works through a Raspberry Pi 4, which will utilize an existing algorithm to detect the movement of lips and translate them into a text format. The device will be controlled through Bluetooth over an app, and that in which will also output the text from the transcription. This provides many benefits for the users, which helps people with hearing impairments and enables them to have more fluid conversations, especially in high background noises environments. And also, it ensures usability, helps the project to be available to a wider variety of people with hearing impairment, allowing more people to benefit from the project.
So the following objective tree shows our design requirements specifications. We determined that the four main requirements should be comfort, user-friendliness, adaptability, and cost. For comfort, we want the system to be easily accessible and not an hindrance. For user-friendliness, we want a comprehensible user interface, as well as the ability to pair with personal devices easily. For adaptability, we want it to function properly in loud environments, as well as work on every person. And for cost, we just want to provide it at a decent value for all users. And below, we have the weighting of each criteria, and where we determine that adaptability should have the most weight. The following are the market requirements we determined. The first is the camera must be easily transportable and affordable. Then we have that it must be able to connect to different kinds of phones. The app should be user-friendly. the system should be able to function consistently and reliably, and the transcription should be responsive enough to support a normal conversation. This is how the marketing requirements translate to engineering requirements. 4 and 5 require that the processing speed should cover at least 150 words per minute. This was selected so that the system could keep up with the average conversation speed. 1 and 4 require that the power supply should be able to consistently provide 800 milliamps for at least 8 hours. This was determined to be the most current draw necessary for all the individual components of the system. 4 also requires that the lip reading algorithm should have an accuracy of at least 75%. This places it well above a human's 45% capability. And 1, 2, and 3 require that the system should implement an Android mobile app along with Bluetooth Low Energy. So Bluetooth is a low cost and simple way to connect the system together, and Android was chosen as it works on a greater variety of devices. Here is our trade-off matrix where we just compare the market requirements to the engineering requirements. Now for the overall system description, we have the camera that provides the visual input. It gets sent to the Raspberry Pi, which is running the lip reading algorithm and the code necessary to do the communication with the mobile device, which has the text output and runs the Android control app. So far up to this point, we've gotten the camera connected and configured the Pi to be able to run the lip reading algorithm properly. We've also designed and tested a solar charged battery to allow affordable and convenient use of the device. Our further plans are to improve the speed and accuracy of the transcription, as well as developing the app to pair with the device. And some related theory for the software is that the lip reading algorithm is an end-to-end machine learning process. And this could be broken up into 3 main sections. The first being just data acquisition and preparation. The second is the machine learning model, which includes the training and the testing. And the final is the code for integrating the model into a final result.
Okay, so for the hardware-related theory, this is our overall design currently for our power supply circuit. So overall, it's broken up into 2 sections, separated here by the 6-volt battery. To the right is our main power supply circuit, in which is the 6-volt battery is connected in series with a diode, and that is meant to drop the output voltage to around 5 volts, which is required by the Raspberry Pi. And we are further simulating the cable connecting the power supply to the Raspberry Pi by the resistance of the wire and the resistance of the Raspberry Pi. To the left of the 6-volt battery is our charging circuit. The main component is an LM324 comparator, in which we have our solar panel, which has a max output of 7.2 volts connected to the negative input and the power supply for the comparator. And the negative power supply of the comparator is connected to ground. For the positive terminal input, we have 8 volts being inputted, which is being supplied by the voltage divider circuit, which has a 9-volt battery connected to it. And the overall idea behind the circuit is that so long as the voltage from the solar panel does not exceed 8 volts, the comparator will allow it to output around 6.5 volts, which is sufficient to charge our battery. If the solar panel, for whatever reason, was to exceed 8 volts, the comparator will cut it off and will not allow it to overcharge the battery.
And here's the data flow diagram for our project, which records speech with the camera. And then that video is sent to the lip reading algorithm to be used along with the weights from the pre-trained model to transcribe the text, which is then sent to the mobile app so it can be displayed for the user. And this is our functional decomposition level 1, which is the power supply powering both the camera and the Raspberry Pi. And then the camera can record the person talking, send it to the Pi, which can then transcribe the text to be displayed on the mobile app. And then here's images from our software implementation. So on the left, we have the custom package, which just imports all the Python dependencies. And then to the right, we have the main driver of the Python script of the algorithm. And then the output can be seen on the right here, with the top one being an output video, which is just the input video with what was said subtitled at the bottom. And then the terminal output contains the plain text of what was said.
All right, so this is our hardware implementation. On the left, you can see the complete power supply for the Pi with the two circuits. The left circuit, as Rob mentioned, is a power supply circuit that consists of a 6-volt battery in series with a diode, and that's attached to a USB-C receptacle, which is then connected to the power supply of the Pi. The right is our charging circuit, which consists of the LM324 comparator, which is shown in the middle image, and the voltage divider circuit, which is shown all the way to the right. The solar panel, which is shown on the top of the right, the top right of the left image, is responsible for charging the battery. And as Rob mentioned, is connected to the negative input on the comparator. The 9-volt battery is attached to a voltage divider circuit, which drops the voltage down to 8 volts and then goes to the comparator's positive input. And as Rob said before, as long as the solar panel is lower than 8 volts, the comparator will allow the battery to charge. If the comparator exceeds 8 volts, then the comparator will open the circuit and not charge the battery.
So for our testing results and analysis, our hardware results had the power supply circuit being capable of powering the Pi and running all of its commands. There was an occasional low voltage warning, but it did not affect the output of the system. And currently the solar panel for the charging circuit can't supply enough voltage to efficiently charge the battery. So we'll work on improving that. And for software, currently the Pi is able to transcribe with an accuracy of about 30%, and the transcription is not quite fast enough to support a normal conversation.
Okay.
And then here's a demonstration video.
There you go.
Hello, we're Team eyeMouth, and this is our project for the visual transcription system for the deaf and hearing impaired. The purpose and inspiration behind this project was to create a conversational aid that is able to function in loud environments. Currently, we have our power supply circuit and a Raspberry Pi up and running, and we're going to be doing a demonstration for you.
All right, so the first part is recording the video, and we can see the command here for doing so, where we specify the resolution to be 640 by 360, the FPS to be 30, time 5 seconds, and just naming the output file.
Set blue in A1 again.
All right, so here we have the command to run the program, which is the predict file, which is providing the path to the wait file, as well as the path to the recording file. Here we have the output video, and the text appears. And we have the final result here, the confirmation message, and the text output. So we see that our current results have about a 30% accuracy, but this will be improved upon in our future work. There you go.
Nick, you're muted.
Yeah, sorry. For our go/no-go milestone, for software, we wanted to find a lip reading algorithm that is developed for use with the Raspberry Pi and begin implementing it to make sure the communication is functional. And for hardware, we wanted to find a camera that is compatible with the Pi and determine and design the hardware layout for the power supply. And then as we've demonstrated, we met and exceeded these goals.
All right, so this is our overall cost analysis and bill of materials. We initially started with the cost of about $90, but due to switching from our Arduino microcontroller to Raspberry Pi, as well as getting a more finalized list of all the parts needed to build the power supply, the total cost increased from 90 to about 200. And yeah, this is the list of all our parts to date. All right, to conclude, we feel that our project is in pretty good standing and can be completed successfully. We will work over the winter break and spring semester. For the hardware tasks remaining, we need to find a more reliable and hopefully smaller battery, as our current one is rather bulky. The power supply and charging circuits need to be optimized and condensed to hopefully fit onto a PCB. And on the software side of things, we need to optimize our algorithm because as of now, the algorithm accuracy and the speed is lower than our target goal. We need a method of consecutively running all of our commands, and we plan to make an Android app capable of controlling the Pi through Bluetooth. Here we have our project timeline and Gantt chart that display our layout of completing all the tasks mentioned in the last slide. This will cover the winter break and spring semester. Here are all the codes, standards, and constraints associated with our project. While going about completing the project, we made sure to adhere to everything listed below. Here we have multiple statements concerning the issue of ethics in working as a team and for completing our project. And these are our references for the project to date. This has been Team eyeMouth. Thank you for listening. Any questions?
Okay, it's a very good project and has a high technical merit. The point is that to all the projects besides ethics and societal impact, to mention also about to open a slide to all the projects technical merit, and another slide applications to industry, to highlight the it's very important to highlight the technical merit. Why is technically what components underlies and how applies to industry. So these two slides should be included to the final presentation. Okay, very good job.
Thank you.
Okay, thank you.